Tonight, we are going to follow a small surface mount semiconductor from the first design idea to the moment it rests on a circuit board. We will begin with the object as it appears from the outside, not as a diagram, not as a glowing symbol of the future, not as a fast montage of factories, robots, and bright lights, just as a small, quiet part on a board. It may be a black rectangle with tiny silver leads along two sides, or it may be a flat square package with no visible leads at all, only metal pads tucked underneath. Or it may be a package with little solder balls hidden on the bottom, waiting to meet matching pads on the board. Around it are other parts: small tan capacitors, dark resistors, coils, connectors, copper traces hidden under green solder mask, vias like tiny circular wells, carrying signals from one layer of the board to another. The board may be a motherboard, a daughter board, a sister board, a controller board, or a small module inside a larger machine. The chip package sits quietly among them, but the package is not the whole story. Inside that black body is a much smaller piece of material, the die. The die is the active chip. It is the part that was made on a wafer. It is the part where transistors, contacts, and metal lines were formed layer by layer. The package protects it, holds it, and gives it a practical way to connect to the outside world. That distinction matters. When we hold a surface mount IC, we are usually holding a protected, packaged form of the chip. We are not touching the bare silicon die directly. The actual die is fragile, small, and carefully sealed away. It does not want dust. It does not want fingerprints. It does not want a bend, a scratch, or a careless static discharge. So the black package is a little house for the die. It gives the die a shape that machines can pick up. It gives it edges or pads that solder can grip. It gives it a marking, often with a part number and a small orientation dot. It gives the board designer a known footprint, a pattern of copper pads where the part can land. The board beneath it is also not the chip. The board is a carrier and connector. It is usually made from layers of fiberglass reinforced epoxy laminate and copper. It has traces that run like flat wires between components. It has ground planes and power planes. It has holes plated with copper. It has solder mask to keep solder in its proper place. The board is the quiet town. The IC package is one building in that town, and inside that building is the small active silicon die, where the work actually happens. For this video, we will walk backward from the board to the package, from the package to the die, from the die to the wafer, from the wafer to the silicon crystal, and then forward again through the careful process that brings the part back to the board. Nothing in the story needs to hurry. The chip does not become a chip in one step. It passes through design, purification, crystal growth, slicing, polishing, cleaning, coating, exposing, etching, doping, depositing, testing, cutting, bonding, molding, marking, testing again, shipping, placing, reflowing, and inspection. Each step changes something small. A layer is added. A layer is removed. A pattern is transferred. A region is made slightly more conductive. A contact is opened. A metal line is formed. A die is separated. A package is sealed. A solder joint cools. By the end, the finished component looks simple again. It is just a small black part on a board. But now when we look at it, we can imagine all the quiet exact routines hidden inside. Before we go further, it helps to picture the board under a steady lamp. The surface is not perfectly flat, though it may seem that way at first. Components rise from it in small different heights. Some are so low they appear almost painted onto the board. Others stand a little taller. A connector makes a plastic ridge. A metal shield catches a dull reflection. A larger chip may sit nearby, surrounded by tiny support parts that help it receive clean power, communicate with memory, or pass signals outward. The small, surface-mount semiconductor may have only 3 pins. It may have 8. It may have dozens, hundreds, or more. The number depends on its purpose. A little transistor package does not need many connections. A microcontroller needs more. A memory chip, processor, or communications device may need many more still. But all of them share a practical need. The active semiconductor material inside must be connected to the world outside. The die cannot simply float alone. It needs power, ground, inputs, outputs, and sometimes heat paths. The package and the board do the quiet work of making those connections large enough, sturdy enough, and repeatable enough for manufacturing. This is why surface mount technology is so important. A board assembly line can place many small packages automatically. A nozzle can lift a package from tape, move it above the board, rotate it into position, lower it onto solder paste, and release it. The part may weigh almost nothing, but its placement matters. If it is shifted, rotated, or placed on the wrong footprint, the board may fail. The stillness of the finished board hides all of that movement. It hides the reels, it hides the stencil. It hides the oven. It hides the tests. And far deeper, inside the package, it hides the wafer. That is where we are going. Before we reach the wafer, it helps to pause with the word semiconductor. The word sounds specialized, but the basic idea is gentle enough. A conductor lets electric current move easily. An insulator resists that movement. A semiconductor lives between those two conditions. Its behavior can be guided. It can be made to conduct in one region and resist in another. It can be shaped into pathways, barriers, junctions, and switches. That is why semiconductors are useful. Silicon, the main material in many integrated circuits, is naturally not as eager to conduct as copper and not as stubborn as glass. It has a kind of middle behavior. With the right crystal structure, the right purity, and the right tiny additions of other atoms, selected regions of silicon can become more useful for electronics. Those tiny additions are called dopants. Doping does not mean that the chip is made mostly of those materials. It means that very small controlled amounts of certain atoms are placed into certain regions. Boron may be used to make p-type regions. Phosphorus or arsenic may be used to make n-type regions. The letters P and N are quiet shorthand for how charge carriers behave in that material. The important part for a sleep video is this: the silicon is not simply left alone. It is tuned. It is tuned in patterns. It is tuned by masks, beams, heat, films, and repeated measurements. From those tuned regions, engineers can build devices. One of the most important devices is the transistor. A transistor can act like a tiny controlled switch, or like a controlled valve for current. In digital circuits, huge numbers of transistors can represent information by being on or off, connected or not connected, allowing current or blocking it. An integrated circuit brings many devices together on one die. The word integrated means that the devices and their wiring are made together as a connected system. Instead of building one transistor separately, then another, then wiring them by hand, the manufacturing process creates whole layers of devices and interconnects across the wafer. This is one reason wafers are so important. The wafer is not treated as one chip. It is a shared working surface. The same steps form many copies of a design across it. Each rectangular area may become one die. Later, those dies are separated and packaged. For this episode, we will mostly follow a common silicon integrated circuit, but it is helpful to know that not every semiconductor is silicon. Some devices use gallium arsenide, some use gallium nitride, some use silicon carbide. Those materials can be useful for radio frequency circuits, LEDs, power electronics, high voltage, high temperature, or other special jobs. But silicon is our main path tonight. Silicon is abundant. It can form a strong crystal. It can grow a useful oxide. It can be processed with great precision. It has decades of manufacturing knowledge around it. It is not the only semiconductor, but it is the familiar ground for many integrated circuits. So when we say a chip is made of silicon, we are giving the short version. The longer version is softer and more accurate. A chip may be built on a body of single crystal silicon. Inside and above that body are doped regions, glass-like oxides, other insulating films, metal contacts, metal interconnects, barriers, liners, and protective layers. Around the die are package materials. Under the package are solderable connections. It is a small layered landscape. Some parts conduct, some parts insulate, some parts protect, some parts connect, some parts simply hold everything still. And the whole object begins long before the package reaches the board. The beauty of a semiconductor is that its behavior is not only in the material and not only in the shape. It is in the controlled combination of both. A copper wire conducts because copper is a good conductor and because the wire gives it a path. A plastic case insulates because the material resists current and because it surrounds what it protects. A semiconductor device is more subtle. It can contain regions that conduct under one condition and block under another. A small voltage at one place can influence current somewhere else. A boundary between differently doped regions can create a junction. A thin, insulating layer can allow an electric field to control a channel beneath it. This is why the manufacturing steps are so careful. If a doped region is too shallow, too deep, too wide, or too narrow, the device changes. If a gate is misplaced, a contact fails to land, a metal line is too thin, or an insulator has a defect, the circuit may not behave. The invisible geometry matters. For a listener drifting toward sleep, we do not need every equation. Silicon begins as a crystal. Selected regions are changed by dopants. Thin films cover the surface. Light draws patterns. Etching opens spaces. Metals make routes. Insulators keep routes apart. The result is a device that can guide current with extraordinary control. In daily life, that control becomes almost invisible. A sensor reads a temperature. A memory stores a bit. A regulator smooths a voltage. A controller waits for a button press. A communications chip sends and receives signals. A processor performs instructions too quickly for the eye or ear to follow. But underneath all of that speed is a quiet physical structure, built slowly. That structure begins on a wafer. The word wafer is one of the most important words in this story. A wafer is a thin, flat, polished slice of semiconductor material. In the path we are following, it is a slice of single crystal silicon. It is round because it was cut from a round crystal ingot, a long cylinder grown slowly from molten silicon. Before it is processed, a wafer can look almost too simple. A thin disk, smooth, reflective, gray or silver in the light. Sometimes it catches soft colors on its surface. Sometimes it looks like a dark mirror. But it is not just a shiny disk. It is a carefully prepared foundation. The flatness matters, the cleanliness matters, the crystal orientation matters, the diameter matters, the thickness matters, the number of defects matters. Even the way the surface has been polished matters, because later steps will depend on layers only a little bit thick, and patterns far too small to see with the eye. A wafer is not a finished chip. It is the place where many chips are made together. Imagine a large round tray that can carry hundreds or thousands of repeated rectangles. Each rectangle is a future die. The same process steps are applied across the wafer, but each die area receives the same design pattern. When the wafer is finished, it may look like a grid of tiny city blocks, each one holding a copy of the circuit. The wafer lets manufacturing happen in parallel. Instead of making one chip at a time, the fab works across a whole wafer. Coat the wafer, expose the wafer, develop the resist, etch the exposed regions, remove the resist, clean the wafer, deposit a film, polish it, dope selected regions, heat it, measure it, repeat. Layer after layer, the wafer carries many future dies through the same quiet routine. This is part of why chip manufacturing can be both very precise and very large. The individual features are tiny, but the production flow is organized around wafers, cassettes, tools, and repeated recipes. The wafer has to survive many steps. It may be heated, it may be cooled, it may be spun, it may be exposed to gases, plasmas, liquids, and vacuums. It may be moved by automated handlers from one tool to another. It may rest inside a cassette with other wafers, each one separated and protected. A fab is designed around that careful movement. The wafer is not tarried casually. It is not touched by bare hands. Cleanroom routines exist because a speck of dust can be enormous compared with the patterns being made. A tiny particle in the wrong place can block a pattern, create a short, open a gap, or ruin a die. The wafer must also be clean in a chemical sense. Its surface is prepared again and again. Native oxide may be removed, new oxide may be grown, films may be deposited with careful thickness. Every layer becomes the surface for the next layer. So, when people talk about wafers in the news, they are often talking about much more than a raw material. They are talking about the main production object in the fab. A wafer is the physical schedule of the chip. It holds the work as it moves from blank polished disk to pattern, tested, diced, packaged devices. Tonight our wafer begins before the fab. It begins with silicon itself. A wafer can also help us understand scale. From a distance, the wafer is large enough to hold in two hands, though in a fab it would not be handled that way. Up close, its surface holds details too small to see. Across the round disk, the future dies repeat in rows and columns, but the edges of the circle mean not every position can hold a full rectangular die. Some partial patterns near the rim may never become usable chips. The useful dies sit within the round boundary. The wafer is also expensive in a quiet, accumulated way. Its value grows as it moves through the process. A blank wafer already represents purification, crystal growth, slicing, and polishing. A partly processed wafer represents many tool steps. A nearly finished wafer represents weeks of work, many layers, and many chances for something to go wrong. This is why handling is so careful. A dropped wafer is not simply a broken disk. It is lost time, lost material, lost machine capacity, and lost future components. The wafer's roundness is practical, not decorative. The cylindrical crystal growth produces a cylinder. and a cylinder sliced crosswise gives round wafers. The notch or flat on a wafer can show orientation. Orientation matters because the crystal has directions, and manufacturing uses those directions. The wafer is not a random solid. It is an ordered crystal surface, prepared for ordered patterns. Even when a wafer looks blank, it has a front side and a back side. It has a surface condition. It has a known type. It may be lightly doped already, depending on the wafer specification. It may have a resistivity range. It may have oxygen content, thickness, bow, warp, and many measured qualities that only become meaningful because later processes need consistency. This is one of the quiet lessons of semiconductor manufacturing. Ordinary words like flat, clean, smooth, and pure become very serious words. Flat means flat enough for lithography focus and layer building. Clean means clean enough that microscopic particles are controlled. Smooth means smooth enough for films, gates, and interconnect layers. Pure means pure enough that electrical behavior is not ruined by unwanted atoms. The wafer is a simple shape with demanding standards, and soon it will stop being blank. There is a familiar phrase in chip making, from sand to silicon. It is a useful phrase, but only if we treat it gently. An integrated circuit is not made from ordinary beach sand in any simple, direct way. A fab does not pour sand into one end of a machine and receive finished chips from the other end. The story begins with the chemistry of silicon and oxygen, but the real manufacturing path requires purification, crystal growth, wafer preparation, and a long series of controlled steps. Many sands contain silicon dioxide. Quartz is also silicon dioxide. Glass is often based on silica too. This is why the sand connection is memorable. The raw earth has a material family that can lead toward silicon. Some parts of the process are glass-like. Silicon dioxide can be grown or deposited as an insulating layer. Quartz can be used for masks or reticles in photolithography. Glass fibers can be part of common circuit board laminate. But the active die is not simply a piece of glass. Its main body in our common path is single crystal silicon. Single crystal silicon means that the atoms are arranged in a continuous crystal structure. This is very different from a random grain of sand, and different from ordinary glass, which lacks that same long-range crystal order. The order of the silicon crystal helps make the electronic behavior predictable. A finished IC is not just silicon either. Silicon is the body, the foundation, the quiet plane where the devices are built. But the useful circuit depends on many other materials. Dopants are placed into selected regions. Oxides and other dielectrics insulate one part from another. Conductive materials form contacts down to the silicon. Metal layers form the interconnects that carry signals and power. Barrier materials keep metals where they belong. Protective films guard the surface. Then the die is packaged. The package may include a copper lead frame or a small substrate. It may include bond wires made from gold, copper, or aluminum, depending on the package and process. It may include solder bumps. It may include epoxy mold compound. It may include a heat spreader, lid, thermal pad, or exposed metal paddle. Its outside shape depends on how it will be mounted to the board, so the complete object is layered in more than one sense. There is the silicon die with its microscopic layers. There is the package around the die. There is the solder joint beneath the package. There is the circuit board below that, with copper traces inside a laminated body. The motherboard itself is not a semiconductor. It is usually a printed circuit board, often made from fiberglass reinforced epoxy laminate, with copper layers that route connections between parts. The board supports the semiconductor packages. It powers them, it carries their signals. But the board does not do semiconductor switching in the same way the die does. It helps to say what the IC is not, because the simple phrases can make the object feel magical. It is not a piece of window glass. It is not a small block of metal. It is not a handmade single switch. It is not only the black plastic package we can see. It is a carefully built device, made from purified crystal, modified by dopants, shaped by light, etched by chemistry and plasma, connected by metals, protected by package materials, and finally joined to a board with solder. That is the quiet material truth beneath the familiar phrase. From sand to silicon is a doorway into the story. The real story is slower, and that is where we are going next. Let us take the materials one at a time. Silicon is the main semiconductor body in our path. It is chosen because it can be purified, crystallized, oxidized, and processed with great control. It is not soft like solder. It is not flexible like a circuit board laminate. It is a brittle crystalline material. A bare die can crack. A wafer can break. This is one reason the later package matters so much. Silicon dioxide is an insulator. It can be grown on silicon by oxidation, or deposited in different ways depending on the process. It is glass-like in the sense that it is related to silica and can act as an insulating film, but calling the whole chip glass would be misleading. The oxide is one layer or family of layers among many. Photoresist is temporary. It is not usually part of the finished chip in the way silicon or metal is. It is applied, exposed, developed, and removed. It behaves like a patterned helper. It protects some regions while other regions are changed. Dopants are present in very small amounts. They are not structural bulk materials like the package body. Their job is electrical. They change the behavior of silicon in selected places. They help create P-type and N-type regions, junctions, wells, sources, drains, and other electrically useful structures. Metals are used for connection. A chip needs local connections down to devices and wider routing across the die. Metal layers are not simply poured onto the surface. They are deposited, patterned, polished, separated by dielectrics, and connected through vias. In different technologies and eras, materials can differ. Aluminum has been important. Copper is common in many advanced interconnect systems. Tungsten can appear in plugs or contacts. Barrier materials may keep metals from diffusing where they do not belong. Package materials have their own quiet work. A lead frame can provide mechanical support and electrical paths. A substrate can route tiny die connections outward. Mold compound protects the die. A thermal pad can help heat leave. Solderable finishes make board assembly possible. Solder is yet another material. It belongs mostly to the board assembly stage. Solder does not make the transistor. It joins the package to the board. It forms the final metal bridge between component contacts and copper pads. So, if someone asks, is it sand or glass? The best sleepy answer is, it begins with the idea of silica, quartz, and sand, but it becomes purified single crystal silicon. Some glass-like oxide layers are part of the process. The finished IC is a layered manufactured object, not sand and not glass. That sentence gives us the doorway and the correction together. Before there is a wafer, there is a crystal. Before there is a crystal, there is purified silicon. The path begins with silicon compounds, often associated with silica and quartz. The material must be refined until it becomes suitable for electronic use. Ordinary impurities that might not matter in a window pane or a stone can matter greatly in a semiconductor. A few unwanted atoms in the wrong place can change electrical behavior. So the material is purified. Eventually, the process reaches high-purity polycrystalline silicon. Polycrystalline means many small crystal regions, not one continuous crystal. It is useful feedstock, but it is not yet the single crystal wafer we need. To grow a wafer crystal, purified silicon can be melted in a carefully controlled system. In the Czochralski method, high-purity silicon is heated until it melts. A small seed crystal touches the surface of the melt. The seed has a chosen crystal orientation. Slowly, carefully, it is pulled upward while rotating. The silicon solidifies onto the seed. As the seed rises, a cylindrical crystal forms beneath it. This is the ingot. The picture is slow and almost meditative. Heat below, a bright melt, rotation, pulling speed, temperature control, a crystal neck, a shoulder, then a long cylinder, grown with patient precision. The equipment controls many things at once. The melt temperature must be stable. The pulling rate must be controlled. The seed and crucible may rotate. The atmosphere may be controlled. Dopants can be added in carefully measured amounts when a certain wafer electrical type is needed. The goal is not just a cylinder. The goal is a cylinder with a useful crystal structure and controlled properties. After growth, the ingot is cooled and prepared. Ends may be removed. The diameter may be ground. Flats or notches may be added to show orientation. The ingot is sliced into thin wafers, often using precision wire saws. Slicing creates surfaces that are not yet ready for chip making. They need more preparation. Each wafer may be lapped, etched, cleaned, and polished. Polishing is one of the quietest but most important images in the whole process. The wafer surface becomes mirror smooth. It becomes flat enough for the later layers and patterns. It becomes a surface that can receive films only a tiny fraction of a human hair in thickness. A finished blank wafer may look simple again. The long crystal growth process has become a round, thin disc. But inside that disc is a continuous crystal order. Its surface is ready, its thickness is controlled, its orientation is known. It can now enter the fab. The wafer has not yet become a chip. It is more like a clean page, but unlike an ordinary page, it will not be written on with ink. It will be written on with oxides, photoresist, light, ions, plasma, metal, and heat. The crystal growing stage is a reminder that semiconductor manufacturing begins with patience. The seed crystal does not pull the ingot upward quickly. If the process is too careless, the crystal may not form as needed. The diameter must be controlled. The temperature gradient matters. Rotation helps keep conditions more even. The equipment is designed to keep the melt and the forming crystal in a narrow range of acceptable behavior. There are variations and alternatives. Float zone refining can create very high purity silicon for certain needs. Different wafer specifications exist for different devices. Some wafers are lightly doped, some are more heavily doped. Some have epitaxial layers grown on top. Some are used for power devices, some for logic, some for sensors, some for memory, and some for research or special processes. But for our calm path, the important image remains clear. Purified silicon is turned into a single crystal. The crystal becomes a cylinder. The cylinder becomes slices. The slices become polished wafers. The wafers become the shared surface for many future chips. After slicing, the wafer's surface carries mechanical damage from the cutting process. It cannot simply go straight into delicate device fabrication. Lapping and grinding help shape it. Chemical processes can remove damaged material. Polishing brings the surface into the mirror-like condition needed for later steps. This preparation may sound less glamorous than lithography, but it is essential. A poor surface would affect everything above it. Every later film rests on what came before. Every pattern depends on the surface being ready. When the blank wafer is inspected, it may be checked for thickness, flatness, particles, defects, crystal quality, and other specifications. Only wafers that meet the required standards move forward. Then the wafer is no longer just a material. It becomes work in progress. Long before the wafer reaches a cleanroom tool, the chip begins as a design. Someone must decide what the circuit is supposed to do. It may be a microcontroller. It may be a memory device. It may be a power management IC. It may be a sensor interface, a clock chip, a network chip, a small logic device, or a support chip on a motherboard. The outside package may look similar for many of these parts, but the internal design can be very different. What signals come in? What signals go out? What voltages are expected? How much current can be handled? How fast the circuit must respond? How much power it can consume? How much heat it may produce? How many pins or pads it needs? What package it will fit into? What board footprint the customer may expect? Engineers create circuit descriptions and schematics. They simulate behavior. They check timing, voltage margins, noise, power, and temperature. Digital circuits may be described with hardware description languages. Analog circuits may be drawn and tuned carefully. Memory arrays may be laid out with repeated cells. Power devices may need special structures to handle higher voltages. Eventually, the design must become geometry. The geometry is the layout. The layout tells where each device region, gate, contact, via, and metal route belongs. It is not a picture meant for human decoration. It is a manufacturing instruction broken into many layers. Each layer corresponds to a part of the process: a transistor layer, a well layer, a contact layer, a metal layer, a via layer, another metal layer, protective layers, openings for bond pads. The exact set depends on the process. The layout is checked against many rules. Lines must not be too narrow. Spaces must not be too tight. Contacts must land where they belong. Metal must carry enough current. Heat must be managed. Signals must arrive in time. The circuit must connect as intended. When the design is ready, mask data is prepared. Masks or reticles are templates used in photolithography. They carry the patterns that will be transferred onto the wafer. They are not the chip themselves. They are more like the careful stencils of light used to create the chip layer by layer. The masks must be made with extraordinary precision. Each one corresponds to a layer or patterning step. In the fab, the lithography tool will project light through the reticle, reduce and focus the pattern, and expose the photoresist on the wafer. This means a design mistake can be very expensive. If the masks are wrong, the wafer will faithfully receive the wrong pattern. So verification is slow, detailed, and serious. In a sleek documentary, this stage can feel like a quiet drafting room. The chip has not yet become material. But the instructions already contain the future pathways where current will move. They contain the quiet places where transistors will switch, where signals will rise and fall, where power will enter, and where outputs will leave. The wafer waits for those instructions. Design also includes the package and the board in a practical way. The designers may know that the die must fit in a certain package size. Bond pads or bump locations must match a packaging plan. Some pins may need to carry power, some need to carry ground, some need to carry fast signals, some may be unused, some may need to sit near a certain edge to reduce routing difficulty. The die is small, but its outside connections must eventually become physical pins, pads, or balls. That means the internal layout and the external package cannot be treated as completely separate worlds. For a surface mount part, the board designer will later use a footprint. The footprint defines the copper LAN pattern on the printed circuit board. It includes pad size, spacing, solder mask openings, and sometimes thermal pad details. If the package has a pin 1 marker, the footprint must match the expected orientation. If there is an exposed thermal pad, the board may include vias to move heat into internal copper planes. So even at the design stage, the chip is already moving toward the board. The path may be invisible, but it is present. A schematic becomes a layout. A layout becomes mask data. Mask data becomes patterned layers. Patterned layers become a die. The die becomes a package. The package becomes a footprint. The footprint becomes copper on a board. The copper becomes solder joints. The solder joints become a working assembly. This chain is why manufacturing is both digital and physical. The chip begins as information, but it must survive every material step. A design can be beautiful on a screen and still fail if it cannot be manufactured, packaged, cooled, tested, or soldered reliably. In the quiet hours of engineering, people check all of this. They run design rule checks. They run layout versus schematic checks. They simulate corners, temperatures, voltage ranges, and process variation. They review pinouts. They review package drawings. They prepare test structures. They plan how the chip will be measured after fabrication. Only after all that does the wafer receive the pattern. The design is ready for light. Inside the fab, the wafer moves through a clean room. The clean room is designed to control particles, temperature, humidity, and airflow. The clean room suit is mainly there to protect the wafer and process tools from people, because people are dusty from the wafer's point of view. Skin flakes, hair, lint, and ordinary room dust are all far too large for the tiny patterns being made. In some areas, workers may also need other protective equipment for chemicals, heat, or tools, but the familiar cleanroom clothing is largely about contamination control. The wafer travels in protected carriers. It is handled by tools, robots, cassettes, and carefully controlled stations. It may move through hundreds or thousands of steps before it is finished. One repeated rhythm is this: clean, coat, expose, develop, etch or implant, strip, clean again. Photoresist is one of the key materials in this rhythm. It is a light-sensitive coating. A small amount can be dispensed onto the wafer while the wafer spins, spreading the resist into a thin, even film. The thickness must be controlled. The surface must be clean. The coating must be smooth. In photolithography, light carries a pattern from a reticle to the wafer. The reticle holds the blueprint for one layer. The tool projects and focuses the pattern onto the photoresist. Depending on the resist chemistry, exposed or unexposed regions will later be removed during development. The wafer is not exposed just once. The tool steps across the wafer, exposing one die area, then another, then another. Each exposure creates another copy of the pattern. Later layers must align with earlier layers. Alignment marks help the tool know where the wafer is and how the new pattern should sit above the old ones. This is where the chip begins to feel almost like a printed object. But it is not printing in the ordinary sense. It is not ink on paper. It is pattern transfer on a carefully prepared surface, followed by material changes. After exposure and development, parts of the wafer are protected by resist, and other parts are open. The open parts can be etched, or they can receive dopants, or a film can be patterned. The resist is temporary. It guides the process, then it is removed. Layer by layer, this routine repeats. No single step creates the whole IC. Each step does one calm, specific job. A well is defined, an isolation region is formed, a gate area is patterned, a contact opening is made, a metal line is shaped, a via connects one metal layer to another. The wafer becomes more complex while still appearing, from a distance, like a polished disc. The real landscape is now too small to see without instruments. And yet the process remains physical. The wafer is coated. Light passes through a mask. A film changes. Material is removed. Atoms are introduced. Heat rearranges damage. Metal fills an opening. A surface is polished flat again. Manufacturing at this scale can sound abstract, but it is still a series of material routines. Quiet routines repeated with very little tolerance for error. Lithography is often described as printing with light. That phrase is helpful, but it is also worth slowing down. The reticle or mask contains a pattern. The lithography system uses light and optics to transfer that pattern onto the resist-coated wafer. The image may be reduced by the optics. The wafer stage moves with extreme precision. The tool must focus correctly. It must align to marks already on the wafer. It must expose one area, then move to the next, again and again. If the wafer is slightly out of focus, the pattern can blur. If alignment is wrong, layers may miss one another. If the resist is not uniform, the pattern can change. If a particle lands on the surface, it can cast a shadow or create a defect. The cleanroom lighting is often controlled too. Yellow light can be used in lithography areas because some photoresists are sensitive to shorter wavelengths. This gives cleanrooms a quiet amber feeling in photographs, as if the whole room is working at dusk. After lithography, development reveals the resist pattern. Then the next process step uses that pattern. In an etch step, exposed material may be removed. In an implantation step, dopant ions may enter only where openings allow. In a deposition and lift or Damascene-like flow, patterns help define where conductors or insulators remain. The details differ by process, node, device type, and manufacturer, but the rhythm remains useful for our calm walk. Coat, expose, develop, change the material, clean. Measure. Repeat. As the wafer moves through the fab, metrology tools check results. Film thickness may be measured. Patterns may be inspected. Critical dimensions may be checked. Defects may be mapped. The fab is not simply making the wafer. It is constantly asking whether each step worked. This constant measurement is one reason the process can continue across many layers. Each layer depends on the earlier ones, and each step must stay within limits. Once a pattern exists in the photoresist, the wafer can be changed. Etching removes material. It may use wet chemistry, plasma, or other controlled processes, depending on the layer and the result needed. The resist protects some areas, while exposed areas are removed. Afterward, the resist can be stripped away, leaving the pattern behind in the actual material. Deposition adds material. A very thin film may be grown or deposited over the wafer. It might be an insulating layer. It might be a conductor. It might be a barrier. It might be a layer that will later be patterned and partly removed. Films can be only nanometers or micrometers thick, but they become part of the working structure. Doping changes material. In selected regions of silicon, atoms such as boron, phosphorus, or arsenic may be introduced. These atoms are dopants. They are not added like seasoning in any casual way. They are introduced with measured dose, depth, and location. Ion implantation can accelerate dopant ions into the wafer. Heat treatment, often called annealing, can help repair implantation damage and place dopants into electrically useful positions. The doped regions help form the parts of transistors and other devices. There may be wells, source and drain regions, channels, isolation structures, gate stacks. Exact details depend on the process and chip type. For a sleep-friendly explanation, it is enough to picture the wafer as a flat crystal, where some regions have been carefully taught to behave differently from neighboring regions. Some places will allow current more easily, some places will block it. Some places will respond to an electric field. After the devices are formed, they must be connected. Contacts are openings down to selected parts of the device. A contact can be filled with conductive material so that a transistor region can connect upward to wiring. Vias connect one metal wiring layer to another. Interconnects are the metal lines that route signals and power across the chip. In older or simpler processes, aluminum may be used for wiring. In many modern processes, copper is used, often with barrier materials to keep copper from moving into places where it would cause trouble. Tungsten can appear in plugs or contacts. Different processes use different combinations, and the details can be highly specialized. The important idea is that the chip is not only active silicon, it is silicon plus carefully arranged conductors and insulators. Wires must not short together. Signals must reach the right device. Power must reach every region that needs it. Layers must be separated by dielectrics, then connected only where vias are placed. The structure becomes a stacked city of tiny roads, bridges, rooms, and controlled gates. After many layers, the wafer can be tested. Before cutting it apart, probe equipment can touch test pads and measure whether each die behaves as expected. Some dies pass, some fail. The result becomes a wafer map. Later, good dies can move forward, while bad ones are rejected. The wafer that began as a blank mirror is now filled with future chips. It is ready to be separated. To make the doping idea more physical, picture a region of silicon that will become part of a transistor. The region is not carved like wood. Instead, its electrical character is adjusted. Ions may be accelerated into it. The depth and concentration are controlled. Then heat helps settle the structure into a more useful state. The material still looks like silicon, but electrically it has changed. To make the contact idea more physical, picture an insulating layer over the silicon. The device below cannot be useful unless there is a way to reach it. A small opening is patterned and etched through the insulator. Conductive material fills or lines that opening. Now a path exists from the device region upward to the first level of wiring. To make interconnects more physical, picture layers of tiny metal roads separated by insulating floors. A signal may travel along one metal layer, rise through a via, turn across another layer, and descend again. Power may spread through wider routes. Ground may use broad regions. Fast signals may require careful spacing. Sensitive analog lines may need distance from noisy digital lines. All of this is planned in the layout and realized by the wafer process. The wafer surface may be polished between some steps using chemical mechanical planarization. This helps flatten the surface so later layers can be formed more reliably. Without flattening, the stacked topography could become too uneven for lithography and patterning. Again, the quiet word flat becomes important. Insulators do more than fill space. They prevent unwanted current paths. They reduce unwanted coupling. They hold metal layers apart. In advanced processes, special low-K dielectrics may be used to reduce capacitance between wires. The details can become very deep, but the simple idea is enough. Some materials connect, and some materials keep connections apart. The chip is a controlled argument between connection and separation. Connect this region. Do not connect that region. Let this voltage influence that channel. Keep this metal line away from that one. Open a via here, leave dielectric there. Every useful circuit depends on the calm enforcement of those choices. When fabrication is complete, the wafer may receive passivation, a protective top layer with openings where external connections will be made. Bond pads or bump pads may be exposed. The wafer surface is no longer just a manufacturing surface. The active story inside the die is almost finished. The practical story outside the die is about to begin. At this point in the finished video, the last 40-minute movie begins. The movie may show a cleanroom tool, a wafer surface, a quiet assembly line, or a dark electronics bench. The narration continues, but the picture becomes more continuous and more sleep-like. The wafer is finished enough to be tested. Testing before packaging is useful because packaging costs time and material. There is no reason to package a die that is already known not to work. So, the wafer may go to a probe station. Tiny probe needles or probe cards contact test pads. Electrical signals are sent in, responses are measured. The tester compares the result to expected behavior. The wafer remains whole, but each die can be evaluated. Some dies are good, some are not. A tiny defect may affect one die while nearby dies still work. The result is recorded in a wafer map, a kind of quiet harvest record for the round disk. Good locations are marked in data. Failed locations are avoided later. Then comes dicing. Dicing separates the wafer into individual dies. The grid between dies is called the street or scribe lane. A precision saw, laser process, or other method cuts along those lanes. The wafer may be mounted on tape, so the tiny rectangles remain controlled after separation. What was once a single round wafer becomes many small rectangles. Each die holds the layers formed during wafer fabrication. Each die is still fragile. The edges are newly cut. The surface must remain protected. The tiny pads or bumps must remain clean and usable. The die by itself is not yet convenient for a circuit board. It is too small for ordinary handling. Its connections are too fine. Its surface is too vulnerable. It may need help with heat. It needs a way to survive shipping, placement, soldering, and years of operation. The package is not merely a black covering. It is a mechanical, electrical, and thermal interface. It protects the die from damage and contaminants. It routes microscopic die connections outward to larger leads, pads, or balls. It gives automated assembly machines something repeatable to pick up. It gives the circuit board a known LAN pattern. The die now leaves the wafer story and enters the packaging story. The test stage has a quiet sorting quality. A wafer map may look like a grid of small results. Some positions pass, some fail, some may be binned for different performance levels, depending on the product. The wafer has carried all of its dies together through the fab, but now each die receives its own judgment. This is not unusual. Manufacturing always contains variation. Even in a clean room, not every die will be perfect. A particle, a tiny patterning issue, a defect in a layer, or a process variation can affect one location. The goal is to understand, control, and improve yield while selecting the good devices for packaging. The probe test itself may be automated and quiet. A wafer is loaded, it aligns. The probe card touches pads. Measurements run. The wafer moves. More pads are touched. The tool repeats the sequence until the wafer map is complete. For some devices, testing can be simple. For others, it can be very complex. A memory device may need many cells checked. A processor may need logic patterns. An analog IC may need voltage, current, and noise measurements. A power device may need checks for leakage and breakdown. The exact test depends on the chip's purpose. Once the wafer is approved for dicing, it is prepared so the separated dies do not scatter or become damaged. Mounting tape holds them in place. The cut follows lanes designed into the layout. These lanes are not wasted by accident. They are planned spaces between dies, allowing separation without cutting through active circuitry. After dicing, dies may be picked from the tape. Good dies are selected according to the wafer map. A small tool can lift one die at a time and place it into the next process. Each die is now an individual piece, but still part of a larger manufacturing record. Wafer lot, location, test result, process history. The die is tiny, but the information around it is large. Where it came from, which wafer held it, which tests it passed, which package it will enter. Traceability is part of quiet manufacturing too. Now the die waits for its package. In packaging, the die is attached to something that can support it. For some packages, that support is a lead frame, often copper-based. For others, it is a small substrate with internal routing. The die may be placed with die-attached material. It must sit in the proper position. It may need thermal contact. It may need electrical isolation. It may need mechanical stability. Then the die connections must reach the outside world. One common method is wire bonding. Very fine wires connect bond pads on the die to leads or package features. The wires may be gold, copper, or aluminum, depending on the process. Under magnification, bond wires can look like tiny arcs, rising and falling gently from the die to the frame. Another method is flip chip connection. Instead of wires looping upward, the die may be flipped over, so solder bumps or other connection structures meet pads on a substrate. This can allow many connections and short paths. It can also help with performance and package design. The exact method depends on the chip, cost, current, speed, heat, and package type. Once connected, the die must be protected. Many small IC packages are encapsulated in a mold compound, often epoxy-based. The familiar black package body comes from this protective material. It keeps the die and delicate connections safer from the outside world. It also makes the part easier to handle, mark, test, and mount. Some packages include exposed thermal pads to help heat move from the die into the circuit board. Some use lids or heat spreaders. Some remain very small and simple. Others are complex assemblies with multiple dies, substrates, and heat management features. After molding or enclosure, the package can be trimmed, formed, marked, and tested. Marking may include a part number, date code, lot code, and an orientation mark. For board assembly, orientation matters. A small dot, chamfer, notch, or printed mark may show pin 1. If a chip is rotated incorrectly, its pins may connect to the wrong pads, and the board may not function. The package is tested again because packaging can introduce problems. A wire bond could fail, a connection could be open, a short could exist. The package must prove that the die still works inside its new body. Only then does it become the kind of component that can travel to a board assembly line. The active silicon is now hidden. What remains visible is the practical surface mount part: black body, metal contacts, small shape, quiet purpose. Packaging is sometimes called the second half of manufacturing because a bare die is not enough for most real products. A die can contain the working circuit, but it needs a body and an interface. Without packaging, it would be hard to ship, hard to handle, hard to solder, and easy to damage. Inside the die, connections are microscopic. Outside the package, contacts are still small, but large enough for printed circuit board assembly. The package translates between those worlds. It fans out connections. It gives them spacing. It lets a board designer draw pads, route traces, and plan assembly. Some packages are leaded. Their metal leads extend from the sides. In an SOIC package, the leads curve downward and outward. These leads can be visually inspected after soldering because they remain visible along the sides of the package. Some packages are leadless. A QFN or DFN package may have metal pads exposed on the underside or lower edges. The solder joints are partly hidden after assembly. These packages can save space and help with electrical or thermal performance, but the board layout and solder paste pattern must be correct. Some packages use arrays underneath. A BGA spreads connections across the bottom as a grid of balls. This can support many connections without needing long rows of side leads. But once soldered, the joints are hidden under the package. Package design is full of quiet compromises. Smaller size saves board area, more pins allow more signals. Shorter paths can improve electrical performance. Better thermal pads help heat leave. Lower cost helps production. Reliable solder joints help the board last. No package is only a box. It is a carefully designed bridge between the die and the board. After assembly and package testing, the finished components may be packed in trays, tubes, or tape and reel. For surface mount assembly, tape and reel is common. A long tape holds one component after another in formed pockets. A cover tape seals them in place. The reel can feed into placement equipment automatically. The component is now ready for the board. Surface mount parts are designed to sit on the surface of a printed circuit board. This is different from older through-hole parts, where leads pass through holes in the board and are soldered on the other side. Surface mount technology allows parts to be smaller, placed more densely, and assembled efficiently by machines. There are many surface mount package shapes. An SOIC, or small outline integrated circuit, often has gull wing leads along the sides. The leads bend outward and down, like tiny feet. They rest on copper pads, and solder forms fillets along them during reflow. A QFN, or quad flat no-lead package, is flatter. Its contacts are exposed pads on the underside or around the lower edges, flush with the bottom of the package. It may have a large exposed thermal pad underneath. From above, it can look like a plain black square. The important metal is hidden where the package meets the board. A BGA, or ball grid array, uses solder balls on the underside. The balls are arranged in a grid. When the board is heated in reflow, the balls melt and form joints to matching pads. Many BGA joints are hidden under the package, so inspection may require X-ray. Small transistor packages, regulator packages, sensor packages, and diode packages may use names like SOT, SOD, DFN, or many other families. Each has its own footprint and assembly requirements. The package choice depends on many needs. How many connections are required? How much heat must leave the die? How much board space is available? How fast the signals are? How much current flows? How the part will be tested? How it will be assembled? How much it can cost? Surface mount parts are often delivered in tape and reel. The reel feeds a pick-and-place machine. Each part sits in a pocket in the tape, protected and oriented. The machine peels back cover tape, picks the part with a nozzle, checks its orientation, and places it onto solder paste on the board. For a sleepy manufacturing image, this stage is wonderfully repetitive. Pocket after pocket, part after part, a nozzle lowers and rises, a board moves a small distance. A package settles onto gray solder paste. Nothing is final yet. The paste is sticky enough to hold parts in place, but the true metal joint has not formed. That happens in reflow. Before reflow, the board is a careful arrangement of parts, resting on paste. After reflow, it becomes an electrical assembly. Surface mount packages also need footprints that match them. The footprint is the copper pattern on the board. If the pads are too large, too small, too close, or too far apart, soldering can become unreliable. If the thermal pad design is wrong, the package may not shed heat as expected. If solder paste is applied poorly, a leadless package may float, tilt, or create voids under a thermal pad. The stencil is part of the package story too. It controls how much solder paste lands on each pad. Too little paste can create weak or open joints. Too much paste can create bridges or lift the part. Different packages may need different stencil openings, paste volumes, and board pad designs. This is why manufacturers publish package drawings and assembly recommendations. The board designer and assembly house need the exact dimensions and process expectations. The same black square package shape can have many variants, pitches, pad counts, and thermal designs. A tiny orientation mark is another quiet detail. Many ICs are not symmetrical in their electrical pinout. Pin 1 must land on pad 1. On a board, a small silkscreen mark, copper shape, or assembly drawing may show orientation. On the package, a dot, bevel, notch, or printed mark may show the same thing. During assembly, cameras and software help confirm that the part is rotated correctly. Tape and reel packaging supports this automation. The orientation in the tape is known. The feeder advances the tape by a set pitch. The placement machine knows where the next component should be. A nozzle picks it up. A camera may inspect the component from below. The system corrects for small position errors before placement. The result is both delicate and industrial. The parts are tiny, but the rhythm is steady. The machine moves quickly in real life, but in our sleep video, we can imagine it slowly. A reel unwinds. The cover tape peels back. A nozzle lowers. A component lifts. A camera checks. The board waits. The package lands. Then the next one, and the next. Each surface mount part is a small promise that later heat will complete. A motherboard or other circuit board begins as layers of insulating material and copper. Common boards often use FR4, or similar fiberglass reinforced epoxy laminate. Copper is patterned into traces, pads, planes, and vias. The green surface many people recognize as solder mask, a protective coating that leaves pads exposed where solder should wet. Before surface mount parts are placed, solder paste is applied. A stencil, usually a thin metal sheet with precise openings, is aligned over the board. Solder paste is wiped across it. The paste passes through the openings and lands on the pads. When the stencil lifts, small deposits remain behind. Solder paste is not just liquid metal. It is a mixture of tiny solder alloy particles and flux. At room temperature, it can look like gray cream. It holds its shape for a time. It helps parts stay in place. During reflow, the metal particles melt, the flux helps clean surfaces, and the solder wets the pads and package contacts. The pick-and-place machine then places components. Reels feed parts. Nozzles pick them up. Cameras inspect them. The machine rotates and positions each part. Large components, small capacitors, resistors, connectors, and IC packages all find their places. Then the board enters the reflow oven. The temperature rises according to a controlled profile. The board preheats. The flux activates. The solder reaches its melting point. The tiny deposits become liquid joints, wetting the copper CADs and the metal contacts of the component. Then the board cools. The solder solidifies into strong electrical and mechanical connections. This is the moment the packaged semiconductor becomes part of the board. The die is inside the package. The package contacts are joined by solder. The solder connects to copper pads. The pads connect to traces and planes. The traces lead to other components, connectors, power sources, memory, processors, sensors, or whatever the board is meant to do. After reflow, inspection begins. Automated optical inspection can check placement, polarity, visible solder joints, and missing parts. Hidden joints, like those under BGA packages, may need X-ray inspection. Electrical testing may verify continuity, programming, voltage rails, communication buses, and functional behavior. If the board passes, it can move on. It may be installed in a computer, a router, a medical device, a vehicle module, a sensor, a household appliance, or a quiet piece of equipment no one thinks about unless it stops working. And the small IC returns to the simple image from the beginning. A black package on a board, inside it, a die made from a polished wafer. Inside that die, regions of silicon shaped and tuned by doping. Above those regions, contacts and metal layers. Around the die, protective package material. Beneath it, solder. Beneath the solder, copper. And all around it, the stillness of a finished assembly, waiting for power. When power arrives, nothing visible may happen. Signals move through copper traces. Voltages settle. Clocks begin. Transistors switch. Current passes where it should and stops where it should. The little package performs its ordinary hidden work. For the final moments, there is nothing more to explain. Only the quiet board. The soft equipment hum. And the long path from silicon wafer to motherboard, resting at last in its place. The reflow oven is a useful place to slow the story almost all the way down. The board enters with paste that has not yet become solder joints. The components are placed, but they are not fully joined. The paste holds them gently. The oven's heat follows a profile chosen for the board, the solder alloy, and the components. It is not simply as hot as possible. Too little heat may leave poor joints. Too much heat can damage parts or the board. The shape of the heating and cooling curve matters. As the board warms, flux begins to do its work. It helps prepare metal surfaces for solder wetting. The tiny solder particles in the paste approach their melting range. At reflow, the solder becomes liquid. Surface tension helps pull many parts into alignment if the pad design and paste deposits are correct. Then cooling turns the liquid solder into solid metal joints. In a leaded package, those joints may be visible as small curved fillets. In a QFN, much of the joint may be hidden under the package edge or thermal pad. In a BGA, the joints are hidden beneath the body. This is why different inspection methods exist. A camera can see some things, X-ray can see others, electrical test can reveal still others. The finished board may also be cleaned, depending on the flux chemistry and process. It may be programmed. It may receive conformal coating. It may be screwed into a housing. It may be connected to cables. It may be tested under load. It may run through a burn-in or stress process for some applications. But our small semiconductor has reached the place we promised. It began in design. It became patterns. Those patterns became masks. The masks guided light. Resist, guided etching, and doping. Doping tuned silicon. Contacts reached the devices. Metal layers connected them. The wafer was tested. The die was cut. The package protected it. The surface mount shape made it placeable. Solder joined it to copper, and the copper joined it to the larger board. The final board is a collection of many such stories. Every capacitor has its own material history. Every resistor has its own manufacturing path. Every connector, screw, shield, and trace has a reason. But tonight we followed the semiconductor because it carries a particularly delicate chain from refined crystal to useful circuit. In the last quiet seconds, the movie continues without words. There may be the dark gleam of a wafer. There may be a slow conveyor. There may be a soft clean room light. There may be a finished board resting under a lamp. The narration ends before the video ends. The ambience remains. The small package stays still. And the work inside it continues silently, too small to see, but no longer mysterious. Before the narration gives way to the final quiet ambience, we can let the whole path pass by once more, slowly, in order. The finished board rests in low light. A small package sits on its copper pads. The package looks plain from above, but it is the last visible layer of a long manufacturing story. Inside the package is the die. Inside the die are devices. Inside the devices are regions of silicon whose behavior has been changed with great care. And beneath all of it, at the beginning of the path, there was a wafer. The wafer began as a polished slice of single crystal silicon. It was not glass, though glass-like oxides would become part of the story. It was not beach sand, though silica and quartz give us the familiar starting idea. It was not a metal plate, though metal would later make the contacts and wiring. It was a flat, round, prepared crystal surface, clean enough and orderly enough to receive patterns far smaller than the eye can see. The wafer entered the fab as a quiet foundation. It was cleaned, it was coated. It was exposed to patterned light. It was developed. It was etched. It was implanted. It was heated. It was coated again. It was measured. It was polished. It was carried onward. The wafer did not become complicated all at once. It became complicated by repetition. A small step here, a thin film there, a pattern opened, a region changed, A metal route formed. An insulating layer covered it. A via connected it upward. Another metal layer crossed above. The process made many copies at once. Across the wafer, rectangles repeated. Each one held the same planned circuit. Near the center, the rectangles sat neatly. Near the curved edge, some spaces could not hold a full die. The round wafer carried the rectangular designs as far as it could. The chip design had been prepared before any of this happened. Engineers had defined what the circuit should do. They had checked the schematic, the layout, the timing, the power, the pins, the package, and the rules of the manufacturing process. The masks and reticles carried those decisions into the fab. Light did not invent the circuit. Light transferred the pattern. The material steps made the pattern real. The silicon received dopants in selected regions. Those dopants were not the main bulk material. They were tiny, controlled additions. Boron, phosphorus, arsenic, and other dopants in different contexts can tune the semiconductor. They can help make p-type and n-type behavior. They can help form the source and drain regions, wells, junctions, and other useful structures that allow the device to guide current. Insulators kept one thing from touching another. Conductors made paths where paths were needed. Contacts reached down to the device regions. Vias reached between wiring layers. Interconnects carried signals and power across the die. The IC became a stacked structure of decisions. Connect here, separate there, open this region, protect that one, let current pass under these conditions, block it under those conditions, carry the signal upward, bring that power rail across. When the wafer was finished, it still held many dies together. Testing touched them before they were cut apart. A probe card met tiny pads. Signals entered. Measurements returned. Good dies were recorded. Failed dies were avoided. The wafer map became a quiet list of which little rectangles were ready to continue. Then the wafer was diced. The round object became many separate dies. Each die was a small piece of the larger pattern. Each one had traveled through the fab with its neighbors. Each one had received the same layers and the same careful processing. Now each one could begin its own packaging path. A bare die is powerful but not convenient. It is fragile. It is small. It is hard to handle. It needs protection from the ordinary world. So, the die was attached to a lead frame or substrate. Its pads were connected outward by fine wires or by flip chip structures. It was encapsulated, sealed, marked, trimmed, formed, inspected, and tested. The active silicon disappeared from view. A practical component took its place. That practical component might be an SOIC with visible gull-wing leads. It might be a QFN with flat pads underneath. It might be a BGA with a grid of solder balls hidden below. It might be a tiny SOT package holding a simpler semiconductor device. It might be a power package with an exposed thermal pad. Every shape had a reason. Every reason came from a balance of space, heat, cost, connections, assembly, and reliability. Then the surface mount component reached the board line. The board was prepared with copper pads and solder mask openings. A stencil laid solder paste onto the pads. The paste held its small gray shapes. Placement machines picked components from reels and trays. The black package was lifted, inspected, rotated, and set down. At that moment, it was almost connected, but not quite. The solder paste still needed heat. In the reflow oven, the board warmed. The flux worked. The solder particles melted. Liquid solder wetted the pads and the package contacts. Then the board cooled, and the solder became solid joints. The component was now part of the board, not symbolically, physically, electrically, mechanically, thermally, in whatever way its package and board design allowed. After inspection and testing, the board could do its own work. It might manage power, it might store information, it might connect a sensor, it might help a computer start, it might sit on a daughter board, a sister board, or a motherboard, doing one small job among many. There is also a quiet handling story after assembly. A finished board may move through racks, trays, or anti-static bags. It may be handled by its edges so fingers do not touch contacts. It may receive labels, serial numbers, or test records. It may be powered on by a fixture that touches test pads with spring pins. The fixture may check voltages, load firmware, read identification, or confirm that communication lines respond. For the semiconductor package, these tests are no longer wafer tests or package tests. They are system tests. The chip is now being judged as part of a larger assembly. It depends on the solder joints beneath it, the board traces around it, the power supplied to it, and the other components that share the board. Sometimes the board may fail for reasons that are not inside the IC at all. A solder bridge may connect two pads. A passive component may be missing. A connector may be misaligned. A via may be open. A board may have a scratch or contamination. Manufacturing has many quiet ways to ask the same question. Does the finished object work as intended? If it does, it moves onward. It may go into a larger assembly, then into a housing, then into packaging for shipment. The semiconductor has become almost invisible again. A user may never see it. They may see only a product turning on, a screen lighting, a motor responding, a sensor reading, or a machine waiting calmly in the background. The IC does not know that it began as a wafer. The board does not announce that it carries a patterned crystal. The finished product simply works, which is the final goal of all the careful steps before it. That quiet usefulness is easy to overlook. A person may press a button and think only of the screen. They may plug in a cable and think only of the connector. They may hear a fan start, see an indicator light, or watch a device wake from sleep. But under those ordinary moments are many silent agreements between materials. Silicon agreeing to be tuned, oxide agreeing to insulate, copper agreeing to carry, solder agreeing to join, and the board agreeing to hold everything in place. The path from wafer to board can seem almost impossible because the scales are so different. The wafer is large enough to see and hold. The device features are too small to see. The die is small enough to hide inside a package. The package is large enough for a machine to place. The board is large enough to connect many packages together. The finished product may be large enough to sit on a desk, ride in a vehicle, hang on a wall, or rest inside a machine. The same story moves through all those sizes. Silicon crystal, wafer, pattern, die, package, solder joint, circuit board, system. And if we return once more to the question of what the chip is made of, we can answer it patiently. It is not glass, though it may contain glass-like insulating oxide. It is not sand, though its story can begin with silica and quartz. It is not simply metal, though metal carries its signals. It is not the black package alone, though the package is what we usually see. It is not the motherboard, though the motherboard gives it a place to work. In the common path we followed tonight, it is built on purified, single crystal silicon. It is modified with tiny amounts of dopant atoms. It is shaped through lithography and etching. It is connected through contacts, vias, and metal interconnects. It is insulated by oxide and other dielectric layers. It is protected and presented to the world by package materials. It is joined to the board by solder. But a long answer suits a quiet subject. The small black package no longer needs to be mysterious. It can remain plain. It can remain still. We can know that inside it is a layered die. And before that die there was a wafer. And before that wafer there was a crystal. And before that crystal there was refined material drawn from the ordinary chemistry of the earth. The story has come all the way back to the board. The traces wait under solder mask. The vias pass between layers. The resistors hold their values. The connector waits for a cable. The semiconductor package rests on its pads. Power may arrive now or later. The work inside will still be silent. The transistors will not make a sound. The metal lines will not glow. The wafer will not be visible anymore. Only the finished board remains, calm and complete. And for the last quiet space, the narration can stop. The movie can continue. The small IC can sit in the dim light, having traveled from silicon wafer to motherboard and finally into stillness. And if the board is never opened again, the story still remains inside it. The wafer is gone as a wafer, but its pattern survives. The crystal is no longer visible, but its order is still doing work. The package gives no hint of the clean room, the polish, the masks, the dopants, the contacts, or the solder paste. It simply rests there, one quiet component among many, carrying a long manufacturing path inside a shame small enough to overlook. That is where we can leave it.